So we just saw a great example of how using requirements and ultimately models of our products and how that can lead to new levels of automation that can bring incredibly sophisticated products like rockets to market much faster than we expected. Another trend affecting test is the increased use of artificial intelligence and machine learning to define the features of a product itself. Now, this incorporation of trained rather than designed behavior is creating all new challenges for design and for test engineers. Put simply, having accurate models of your system and their environment are absolutely crucial going forward in the future. So to learn more about how Samsung is using artificial intelligence and machine learning in the design of their next generation wireless networking equipment, please help me welcome to the stage Dr. Sunghyun Choi from Samsung Research. All right, so it wasn't that long ago that I got my 5G phone, and I know backstage we were already talking about 6G. Right. So what is on the horizon for 6G?
Yeah, so ever since the first mobile telephone call in the early 70s, the last 5 decades have produced a revolution in the advancement of mobile communication. Although it might look like we are just getting 5G now, we at Samsung Research are already working on 6G. Each generation of wireless technology takes about a decade to develop, and we are working towards 6G deployments by 2030. With all the capabilities of 5G, it can be hard to imagine what's next. Thus, I would like to highlight 2 megatrends that will define 6G technology and use cases. First, consider that by 2030, there will be more than 500 billion machines connected to the internet. This will be more than 60 times the world population then, and these machines drive different technical requirements than connecting people. Second, consider that the rapid maturization of AI ML technology in both consumer and enterprise applications. 6G mobile networks will use AI ML in a range of ways, from network planning to optimization of radio RF front end. In the future, mobile will enable new applications for hyper-connected experiences, experiences like truly immersive extended reality, high-fidelity mobile holograms, and even digital replicas. These applications create new technical requirements for 6G. Examples include expanding peak data rates up to 1 terabits per second, while reducing the air latency down to 100 microseconds.
Yeah, it's going to be fun, isn't it?
Yeah.
So what types of technical innovations are going to be necessary to meet these new performance requirements?
Well, to meet these requirements, 6G is likely to employ a wide range of candidate technologies. For example, just as the need for more network capacity has pushed 5G to millimeter wave bands like 28 gigahertz, 6G could push into terahertz or sub-terahertz bands beyond 100 gigahertz. To address signal propagation issues at these frequencies, 6G will also need to evolve antenna and beamforming technologies to overcome the massive path loss. Although there are many areas of study for 6G research, one of those that is most exciting is the use of AI and ML. For example, let's take a look at one of the classic challenges in wireless. That is, wireless signal strength decreases over distance. Although higher power signals can travel longer distances, there are practical limitations to a device producing a high quality and high power signal in a cost-effective manner. If you are familiar with audio applications, you probably observed that the sound can become distorted when you turn up the volume. The same is true for a mobile device RF amplifier. Merely driving up the power level can distort the uplink signal and prevent it from being decoded at the base station. As a result, mobile devices actually back off the transmission power in practical use. This ensures transmission of a clean signal. Because of this, there are several techniques that system designers can use to maximize throughput over distance. One option is to use an amplifier that is capable of distortion-free transmission at higher power levels. Although this enables propagation over longer distances, such an amplifier is typically too expensive for practical use. A second option is to reduce the power of the transmission to reduce distortion. However, by doing so, we limit transmission distance of the system. A final option is to drive the amplifier deep into compression, thus allowing for a distorted output.
Yeah, so now you've got a highly distorted system, and we need to make some sense out of that. So how can artificial intelligence and machine learning help the problem?
Right, so we are exploring techniques that use AI ML technology to correct for distortion at the base station. One of our recent innovations is a technology that we refer to as AI-based nonlinearity compensator, or AI-NC. With this approach, we use an AI algorithm that allows the base station to learn distortion patterns of the mobile transmitter by first receiving a reference signal from the mobile. This algorithm is able to effectively reverse engineer distortion caused by the amplifier and correct the received signal. Note that the distortion pattern should be dependent on the mobile device. The beauty of our engine is that the AI model is trained during the runtime adaptively for each mobile device. Using this approach, we can sustain higher data rates over long distance, better utilize spectrum, and improve power consumption of the mobile device.
Yeah, so I know that your team is familiar in using a number of the NI software-defined radios. So can you talk a little bit about how you use the USRP products to help in this work?
So NI's USRP software-defined radio allows us to test our ideas in the real network using a testbed. In this testbed, the SDR emulates the radio portion of both of the mobile device and the base station. For example, in the base station's receive chain, SDR first receives a signal from the mobile device. The waveform is first equalized and then passed through Samsung's proprietary AI engine. The AI engine reconstructs the jumbled waveform so that it can be demodulated in a usable bitstream. Using this technique, even extremely dense communications waveforms can be demodulated. Note that one of the benefits of NI's SDR is the flexibility. This platform allows us to easily test various configurations across multiple types of antennas and also waveforms. We've already been able to demonstrate a 1.9 times improvement in transmission distance, and we'd like to keep improving.
Yeah, so I think it's incredible. I mean, I think you give us a little bit of a glimpse into the future here, and your team has just done fantastic work. And I want to emphasize the point. How many of you would like your high data rates to go twice as far as they go today? I mean, this is going to be incredibly impactful for our industry. And from talking to you offline, I also know how much this is going to scale to even more advanced waveforms in the future.
Right.
So thank you very much, Dr. Choi. Appreciate it.
Thank you.